Hi, welcome to the course Mathematical Aspects of Biomedical Electronic System Design. I am Rathin Joshi. I am a PhD student at Electronic System Engineering Department, Indian Institute of Science. I will be mainly discussing and demonstrating some of the concept taught by Professor Singh, and also I will be talking about how we can interpret information from obtained different kind of biopotentials. Throughout the course, as regular intervals, I will be supporting the concepts, so signal processing concepts. Like in today's module, we will be touching upon some of the things taught in the first week. So Professor Singh has already given a brief introduction and some explained some types of signal and systems. Anything that conveys an information can be considered as a signal. It can be of it can be a function of more than one variable. In this particular course, for most of the biomedical applications, we will be focusing on one dimensional signal. That one dimensional signal will have mostly time as a independent variable. So in this module, I will be talking about some of the types of signal and moving average system demonstration, which was explained by Professor Singh. So let's see some of the additional types for signal. So Professor Singh has already taught that there are different kinds of signal types like continuous time, discrete times. Also it talked about the properties of system like causality, stability, etc. Here we will see another set of or another types of signal, which is very simple and very frequently used in biomedical signal processing. So they are even signals and odd signals. Okay, so from the name, it is pretty clear that even signal will have somewhat symmetry or equal behavior towards one particular thing, whereas odd signals will not probably have that kind of symmetry. So another question is, can we classify or can we distinguish or can we say that okay, this particular signal is either even or odd? Okay, we will come to that in after our demonstration. So we'll see which kind of waveforms are considered as even and odd. If you can see in your screen, here you see the green trace is cosine wave and which is symmetrical to your y-axis. What does it mean? If you take any value towards the x-axis, okay, you all know that cos pi by 2 is 0, right? Cos 90 degree is 0. Same way cos minus pi by 2 or cos minus 90 degree is also 0. So if you can consider this thing y-axis as your reference, then you will see the mirror reflection in the both sides. So you can see a symmetry with respect to y-axis. That is nothing but if your signal will have a symmetry with respect to y-axis, it will have even, it can be considered as a even signal. Whereas in case of sine wave, the same thing won't hold, right? Sine pi by 2 is, or sine 90 degree is 1, as you all know. Whereas if you can talk about sine minus pi by 2 or sine minus 90 degree, it would be minus 1. So this signal obeys the property shown here. F of t is equal to f of minus f of t. Whereas in cosine wave, it follows the property f of t is equal to f of minus t. We will see quickly how we are getting it. We will see that quickly using MATLAB. So you will get, and we'll see some more examples, so you will get some more idea. So let's see the demonstration. Let's see the demonstration for even odd signals. I have defined some variables. Time variable, which is nothing but minus 20 to plus 20, just to demonstrate the behavior with respect to both side of x-axis. If it is symmetrical to y-axis, it's even signal. If it is symmetrical to origin, it's odd signal. Let's see how it is looking like. So what I'll do, I'll just first plot the x, which is my sine wave. Okay, with that I will also try to make it little thicker. By default it's zero point 0.5 line width, which is difficult to make out and see. Also, let's put it in a red color. Let's see how it is looking like. So this is your x-axis, but in order to check it the symmetry with respect to y-axis here, it's better if we can show y-axis as well. So I will use the function x line of 0. Also I'll give the same I'll give some little less line width, and color being an x-axis and y-axis, I'll put it in a black color. Okay, same I will also draw the next axis as well, which is nothing but your x-axis and y-axis. So if you can see, this is your sine wave. Here if you see, at x is equal to 1, okay, at x is equal to 1, y is equal to 1, whereas here x is equal to minus 1, yeah, y is equal to minus 1. So f of t is equal to a particular value, whereas f of minus t is equal to minus of that particular value. So it is symmetrical with respect to origin. If you can see, whatever shape you are getting, if you consider this as a reference, origin as a reference, you will be getting a mirror reflection of that. So odd signals are generally symmetrical and are symmetrical towards an origin with respect to origin, whereas the even signals are symmetrical to your y-axis. Let's see, I have already made a cosine variable which values are stored in y. So before plotting this thing, in order to, I want to show you the same graph, values on the same graph, so I will give the command hold on, and then I will plot. Again it will come as red only, so let's use a different color. Instead of red, put it a blue, so it will be easy to differentiate. So you can see that the blue colored trace is symmetrical with respect to y-axis, which is nothing but your cosine wave. Let's see one more value, so it would be better and more clear. If you can see here, 3 point, let's keep it as 4. So for cosine value, the value for x is equal to 4 is 1. Same thing if we can check for x is equal to minus 4. Okay, for the blue trace we are talking about cosine wave. So at s is equal to minus 4, if we can, I take this data point, just a second, yeah, it got zoomed out, yeah, x is equal to minus 4, it is 1. So consider the red trace, you observe the value x of 1 is equal to y of 1, whereas x of minus 1 is equal to y of minus 1, which obeys the signal property for odd signal, whereas x of 4 is equal to 1 and x of minus 4 is equal to 1. This holds throughout your x-axis. That's why sine wave is called odd signal and cosine wave is called even signal. Okay, one more question. If I define a variable z, which is a summation of x and y, okay, whether z would be even signal or odd signal. If I define a signal w is equal to x dot y, x into y, okay, I'll do pointwise multiplication, x into y, okay, so whether w would be a even signal or odd signal. Okay, I will plot one of them, other one you can check at as a homework. It's a very small homework, okay, and you don't need MATLAB for that. You can even check it with your Excel as well. What I will do, I will plot the summation of that, because, and you have already seen this graph, so I'll quickly show you the summation of that, how it is looking like. I will first show with the existing graph. You can see this, okay, focus on this trace which is there of magenta color. If you can see, at x is equal to 0.5, it is having maximum value, okay, whereas, and maximum value is nothing but 1.4121, whereas if I consider this trace, okay, magenta trace, and if I try to get the value of minus 0.5, okay, so which is almost 0, if you can see this value, it is e to the power minus 6, right? Somehow its cursor is just little difficult to show, but yeah, it's minus. You can see from this it is almost 0. So yeah, it is 0. So it is not following property for even signal x of t is equal to minus x of t. Okay, and it is also not following x of t is equal to minus x of t. So combination or addition of two even and odd signal may not result in either even or odd signal. And also I wanted to inform or infer that it is not necessary that all the signals can be either even or odd. There exists a set of signal which can be neither even nor odd. In most of the biomedical signals, it will be neither even nor odd signals. Okay, so I hope this is clear. You can check about this multiplication thing in your homework, and yeah, there might be some of the question related to what we have discussed in your assignment as well. So we'll go back to our presentation. So I hope it is clear what is even and what is odd signal, how it is look like. Just remember, even signals symmetrical to y-axis, odd signals symmetrical to origin. So the symmetric point is now clear. I suppose you understood it properly. This is the summation of sine wave and cosine wave. So I hope this question, and you should be able to answer the question. Also, you now know that there are many signals which can be neither even nor odd. And if any signal is given, you should be able to identify whether it is even signal or odd signal. Let's see another type of signals which is very important in terms of frequency analysis as well as Fourier analysis, and which will be covered in detail in subsequent lectures as well. But I just want to give you a brief introduction about these types of signal. So they are periodic signal and aperiodic signal. Okay, you can see I can directly explain with this illustration or this waveform available here as well. These waveforms are repetitive. Okay, the same values is attained after some point of time. So in mathematical term, for any functions f of t, if you can find out this relation for all n belongs to natural number n set, that f of t is equal to f of t plus n into t, then you can consider this particular signal as a periodic signal. Very simple. All sinusoidal signals and sum of sinusoidal signals are periodic signal. It's a very important and very useful problem in terms of Fourier analysis, communication related protocols, etc., to know the fundamental frequency. How to find out a fundamental frequency and what is the importance of that, we will see in subsequent lectures. Also, this particular periodicity, okay, will forms the basis of Fourier analysis. Fourier analysis will be covered in detail in the subsequent sections, be it a Fourier series or Fourier transform, and more importantly, how the analysis with respect to Fourier transform is related to your biomedical data. It is very important for any particular biomedical problem or data to verify it or cross-check it, your physiological signature with respect to a set of frequencies. It will also help to identify what are the signal of interest and what is the noise. We will quickly see one very elementary signal noise removal technique in this particular presentation in the upcoming slides. So just want to ask you, let's consider again the same sum of sinusoid signal. We have seen that it is not symmetrical. It is neither even nor odd signal. But what about periodicity? Okay, so you can see the same pattern is getting repeated. So we can say that yes, the signal is periodic. And as I mentioned, that any particular signal or any like linear combination of sinusoidal signal will be periodic, and it is you should be able to identify the fundamental period. There is a condition, and we will cover that in the subsequent lecture. So I hope this brief I wanted you to glance through this periodicity of a signals, very important property, and we'll come to that. We'll discuss in detail. We'll also see the fast Fourier transform and everything in the future. So yeah, we'll see one more type of data signals, that is a deterministic and non-deterministic signal. Like if I talk about sinusoidal signal, again, if I talk about any particular signal, let's say which is like f of t is equal to t plus 2. So when my t range is defined, okay, I can have an idea at any particular point of t what would be the value of my signal. So that is known as a deterministic signal. Sinusoidal signals are deterministic signals, exponential signals are deterministic signals. In short, for all signals, for the signals which you can identify the value at any point of time, are known as deterministic signal. Whereas there are some other type of signal. If I talk about, as I mentioned, signal is anything which conveys the information. If I talk about rainfall in India or rainfall in any particular city over the period of time, so this is basically a non-deterministic quantity. You cannot at any point of time say what is the how much rainfall would be there at this particular point of time. You can approximate, you can forecast, that is based on your previous data, and that is always a function of your probability. If you see any weather report or something, they'll say expected. Okay, this expectation is there, it's not a certainty. So those signals are nothing but your non-deterministic signal, where you cannot identify. Okay, instead of giving more example, one very recent and appropriate example which all of us are aware and affected in some or the other way is this. Okay, so this graph, if you see, is number of COVID cases in India from February March 2020 till today. Okay, so this graph, nobody can you can approximate, and using this you can say there might be this many cases, there might be third wave, you never know, right? So let's hope it won't be there. But yeah, so you can identify number of cases using this approximation, but you cannot formulate an exact equation, or you cannot provide the future value of the function using this. Okay, so let's also we will see whether this signal what we have analyzed, whether it is randomized signal or not, whether it is deterministic or non-deterministic signal. So we can clearly see that, and we have already have the formula also of this particular equation. So we know that this is not a random signal, this is deterministic signal. Okay, a few more things which I have covered. I'll just quickly tell you. Deterministic signal can be modeled as a mathematical equation. A non-deterministic signal can be approximated or modeled using probabilistic approximation. Okay, one more important point is most of the biomedical signals are aperiodic. Let's just simply think about ECG. Okay, I hope all of you have seen. If not, please go and see how ECG looks like. Okay, it would be periodic, but not exactly periodic. From person to person it differs. If your ECG has an uneven rate, it is a condition which needs to be treated. You should consult a cardiologist. So that ECG signals are aperiodic. Okay, you will be having this kind of PQRS waveforms, but that time window is not certain. It should be in particular range for a healthy human being. Okay, same goes for EEG as well. Just check the EEGs also. They are also random, aperiodic signal, random signal, and etc. Obviously, most of the problems we will consider time as a positive entity unless and until we are taking a reference and observing the properties on both sides. So yeah, most of the biomedical signals are aperiodic, asymmetrical, and random. In this course, we will mostly focus on one-dimensional signals. If time permits, we'll also talk a bit on image analysis or biomedical image analysis, which is a two-dimensional signal. So one more point to notice here, if you can see here, there are two kind of traces. The one is a line, other one is a plot. Okay, actually this all are discrete signal, which is a function of a days, number of days, and at every particular day there are values. Because of too many values on the x-axis, you are able to identify this as a like it is filled or something. So when you have a multiple data and you want to know the trend, now we all know that this is the first wave, this is the second wave. How can we identify that what is the trend, how a particular quantity or signal is changing? For that, here if you can see it, very small letters written 7-day average. Okay, so this particular point corresponds to the previous 7 days, and it is the average of previous 7 days. It will give you a trend. Okay, it will give you how a particular data's behavior or its tendency. Okay, so this is something which has been talked by Professor Singh in the first lecture. It's nothing but your moving average. Okay, so let's quickly see what is moving average. I will also see the demonstration how it will help and everything. So yeah, we'll see the moving average. This moving average can be of different type. When you have a data a sequence already available, you can take one sample before and one sample after along with the present time sample and average it out. It would be a 3-point average. You can also consider 7-point average, 11-point average. How it affects your data, how it is looking like, we'll soon see in the demonstration. But before that, I will just tell you why moving average is required, what is the applications of that. So first of all, most of the biomedical data sets are affected by high frequency noise. If you talk about EEG, ECG, and for some of the signals which are used, they have their own region of interest for frequency. Okay, for EEG, we don't care about the frequencies greater than 100 hertz or something. So in your recording, and which is non-neural, if it is something greater than 100 hertz, first of all, it's very rare in EEG, and if it is there, we need to identify whether that particular signal is because of some artifact or whether it is a neural signal. Okay, also it depends from where you are taking EEG. There are different levels of taking EEG based on the invasivity, whether you are opening the skull and taking EEG or not, whether you are even if after opening the skull, at which level you are taking, and accordingly your range of frequency will differ. The point of interest, or the why I am saying this is high frequency noise removal is one of the very essential and basic step is in any biomedical signal pre-processing algorithm. Okay, so just one of the main point is it will remove the high frequency noise. Now, as it will remove the high frequency noise, most of you should who are familiar with little bit of electronics and filter design, it is considered as a low pass filter. Again, it's a finite impulse response low pass filter, so it has all the advantages which FIR filter has, and easy to realize because it has a finite impulse response. You don't need a lot of hardware to implement it if required. It will smoothen your curve, as the name suggests, it's a filter. It will smoothen your curve. Another important thing, if you can see here, when I'm taking an average of this, it is just considering sample. It is not considering, or it is not getting samples are not getting multiplied by any of the integer 1 2 3 4 5 6. So if it is getting multiplied, there is a model for filter implementation known as MAC, multiply and accumulate. Here we are just accumulating, so it is simple, complexity is less, and that's why it is important in analyzing or analyzing biomedical signals. So what are the applications? Main applications are I have already told you about COVID cases, right? So we can identify the tendency of disease over the period of time, how it is moving, changing. So one of the all the disease burden analysis, it can be used. Already talked about ECG and EEG analysis, it can be used. Most of you would be liking one or other kind of sports, right? So if your favorite players analysis, if you want, you can use this moving average to see in the last previous games how many number of game how he has played, what are his statistics and all. And also this is recently used in many data analysis related to sports. If you are interested in investment in stock markets, etc., moving average is very very known terminology, so it is used there as well. Okay, so let's quickly visualize what I wanted to say. Also, why it is like 3 point, how waveform will be looking like if I use 3 point moving average, how it will be looking like if I use 7 point moving average, how it will be used if I use even 11 point moving average, right? So we should know how it looks like. So let's quickly see the demonstration of the same using MATLAB. Let's quickly see the demonstration for moving average. For that I need to define one particular variable. It should have enough changes or fluctuations to understand this thing in more detail. So for this I have defined this particular variable. You can this it's particularly a random original signal. Okay, let's quickly see how it is looking like, just to verify. Yeah, it has enough number of variations. This can be used as our sample. Okay, still I will add some more. I'll add some, make it little bigger sample to include all type of variations. So I have used a different multiple of the same variable here, as you can see. Yeah, so yeah, it should be 0.4 anyway, that's fine. So let's just quickly see how it looks like. Yeah, it's around 408 samples and it is looking like this. It has enough changes and enough slopes, so we can consider this. It would be good example to visualize. Okay, so also I will show you one more version after adding a particular noise. This is the sequence syntax to add a noise. A data value is very large, so I will just multiply the noise by 3. Okay, so now I will show you both the plots. First let me plot A, that is our original signal. We have already seen this. Let me also draw or also show the version with noise. Okay, so that is nothing but your B. So if I plot that, I can see, yeah, so this is something which is similar to what biomedical signals look like. It will be affected by some noise. It's a random noise. Also very important when we are considering a frequency based analysis, and while talking Fourier FFT, fast Fourier transforms and Fourier analysis, I will be also explaining the frequency response of similar kind of waveform. It is very essential to understand the frequency response of such waveforms. So let's go back and understand furthermore, and we need to verify the moving average system functionality and how different points of moving average will affect your entire original waveform. What we will do is we'll have 3 versions based on moving average. One which is a 3-point moving average, other one is 7-point moving average, other one is 11-point moving average. So you already have your one original signal, that is your A. Okay, then you will have a noise affected signal which is B. Then we will have 3-point moving average, 7-point moving average and 11-point moving average. So let's quickly get those values. So move mean is a function in order to obtain the moving average. Remember, C is 3-point moving average. Okay, D is 7-point moving average and E is 11-point moving average. Okay, so I have defined the C, D and E as different moving average points. So we need to compare this B, C, D, E with respect to A, noise affected signal, and all 3 moving average signals with original signal. So we need 4 plots. So I'm using subplot. Okay, very slowly I'm going because it's a first class, so you should understand how it is looking. Let's just plot A. Okay, also uh, we will decide, let's just plot A first, original sequence. Okay, so out of 4 subplot, first plot we can see the A. Okay, very easy. This is our original signal. What I will do is I will draw it with cyan color or light color, so it would be easy for you people. When I show the next trace on the same plot, you can differentiate between them. This is your input original signal. Okay, remember cyan color is input original signal. Then we will plot this noise affected version in the same plot B, right? B is the noise affected version. Let's draw it with black color. Okay, let's see how it is looking like. Also I will change x limit because I don't want samples more than 408. It will look like a discontinuous trace, which is not, so I don't want more limit or more values on x-axis. Let's just quickly verify how it is coming. You can see in the graph, see this black one is nothing but noise affected, where the cyan one is your original signal. Okay, similarly we will see this comparison for the next all 3 graphs as well. Okay, what do we do here? We will plot the next few graphs, but if you want you can use this kind of different functions related to plot. It is very important to label both the axes. We'll give y label as values. Okay, also all the graphs should have a proper title. So this graph is nothing but your original noise affected signal, and original signal. Okay, similarly so let's just run this so you will have an idea. It has samples, noise affected signal, original signal, values. Now let's see the moving average part with 3 samples, so which is nothing but your C. So this things will remain as it is till this point. We will make the essential change wherever it is required. So first I want to plot A in cyan color only, then I want to plot this as a second subplot, so this should be 2. Okay, then I want to plot C, not B. We have already used black color, so use blue color for this or red color for this. Okay, sample values will remain as it is. This would be 3-point average, right? 3-point moving average. When I write moving average, there are different types of moving average known as weighted moving average, exponential moving average, but this is a simple moving average where we are not multiplying it by any number. I mentioned that MAC thing, right? Multiply and accumulate. Here we are just using a simple moving average, okay, with 3-point. So let's quickly see how that graph looks like. So if you see this red one, okay, is your moving average, whereas this blue one is your original data. Okay, better if I can show you with respect to the noise affected version. Why? Because the change would be evident. Okay, so let's in that case just we'll plot first. We'll see it in all 3 versions. Okay, so what I will do is I want to plot B, so I will store this for now. I will close all the existing figures and then I will give the same command. So now we'll see 3 plots, okay, because the earlier one input data set was almost like straight without any change. So better if we can see it with respect to the one which has noise. It will give more clear idea. Okay, so let's see this first then. So this is your 3-point moving average. You can see your input will have all the variations, whereas your 3-point moving average, it still have some it's not completely smooth, but it is better than what is there in cyan color, your input trace. Okay, similarly we will plot for 7 points. Again, we already did it once, so we will not only do work, we will do smart work. So this is your noise affected version. Okay, consider that as your original signal, because most of the biomedical signals are originally noise affected. Let's plot it in green color. The next one is nothing but your 7 point moving average. So, and that is your D, which I have already changed. This is your 7-point moving average. Okay, let's see this, how it is looking like. So it is much better, right? You can see the smoothness compared to this point, and this point is much more smoother, and some of the variations have been approximated or nullified. So high frequency changes are nullified. Similarly, let's see the next 11-point version as well. A lot of applications are there. It's just a smoothening or low pass filtering, but you are adding more number of samples, which means you are adding more number of terms in your impulse response, which means you are adding, if you want to realize, you need more hardware to implement that. So you are getting a better waveform, but at the cost of additional hardware or more computations. Okay, 3-point version will have simplest computation, less hardware, whereas 11-point will have a lot of hardware, but it will give you better smoothening. It depends, it's a trade-off between you have to decide how much data fidelity or quality of the data you want. Okay, so let's see the third one. Yeah, this is 11-point. It is even much better. You can observe this point, where here it is almost like -10, here it is gone down, here it is even taken further. Smoothness increases when you go from 3-point to 11-point. Very important point. And with respect to the trend remains the same. Okay, further if you go, it will even become smoother. If you go below 2 samples, it will be more sharp. Okay, so this is what basically I wanted you people to visualize or show in terms of 3-point, 7-point and 11-point simple moving average with respect to your noise affected signal. Again, we will come back to this when we will learn FFT, and with respect to this, on this side I will show you the FFT of this. It will give you an idea how the role of the frequency response is getting tuned or modified with respect to the number of sample what you are using. Let's quickly go back to the present. So you have seen the moving average demonstration. So this is something like, it is looking like something like this. Okay, this is another example for another data set which I have used. I would encourage you people to use it. You can use it even using Microsoft Excel or any other simple data computation software. You can generate your data. It's just a random data. So otherwise, if there is some in the future when I will be talking about biomedical data set, I will share the sample data set. I would comment it, or I would include it in the description of this video when this video will be uploaded. So yeah, you can try using this small illustration, understand the moving average. We'll see the impulse response and frequency response and how it changes with respect to FFT in the upcoming lectures. I will see you again with some more demonstration and other topics. If you have any doubts, you can feel free to write in the forum. I would be happy to answer. And once the video is uploaded, you can ask in the YouTube comment section as well, up to you. But yeah, for this course students, it's better if you ask us on the forum, because we will be mainly replying in that forum. I will be checking forum more frequently than when it is uploaded YouTube or anywhere. So I'll meet you again. Till then, all of you please take care, stay safe, bye.